Everyone. Thank you for joining the I²CNER seminar series. The I²CNER seminar series was launched in 2010 upon the inception of I²CNER. Since then, the seminar series has featured the best researchers in the world on carbon neutral energy issues. I'm Jing Wang, and I will be the host today. And today we will have Professor Pedro Sáenz, Pedro is an assistant professor and the director of the Physical Mathematics Laboratory in the Department of Mathematics at UNC. From 2015 to 2019, he was an instructor in applied mathematics at MIT. Pedro received his PhD from the University of Edinburgh in 2014, where I heard about him as a legend. And he was a postdoctoral fellow at Imperial College London with Professor Omar Matar in 2015. And he was awarded an Alfred Slogan Research Fellowship in 2023 and the NSF Career Award in 2021. Pedro also received multiple scientific visualization awards, including the APS Gallery Fluid of Motion Award in 2017 and 2022. And his research blend experiments, numerical simulation, and theory to address fundamental problems that find motivations in physics and engineering. Yeah, so before we begin, I would like to take a moment to remind you that your questions will be addressed after the presentation, and please use raise hand button to or type your question or comments in the Q&A box. So when you are called on, please unmute yourself. And just a reminder that this webinar will be recorded and made available on the I²CNER website. So without further ado, I'd like to welcome Professor Pedro Sáenz to give the talk.
So much. I think I can use this. Thank you, everyone. Thank you for having me. It's a pleasure. I was looking forward to coming here because I work with Danny, Alex, who perhaps some of you know. I did my PhD with them, and they moved to Japan when I went to the US, and they will speak very highly of Japan. So I was looking forward to coming here and meet you all. So thank you for having me. It's a pleasure. I want to try to speak slowly, which I typically don't do. I usually speak very fast. If at some point you see that you don't understand me, please stop me, and I will try to go down because I tend to speak very, very fast. In this talk, I want to talk to you about two things. I started as an engineer. I did mechanical engineering in my undergraduate, and then I did my PhD in fluid mechanics. And then fluid mechanics took me more towards the math side, applied mathematics. So kind of my research now is a little bit of a mixture. We have some problems that are kind of mathematically motivated, in which we are interested in effects driven by curiosity rather than applications. So that's going to be the first part of the talk on walking droplets. In the second half, we started a problem that is more an engineering problem that we discovered 1 year ago. And I'm actually very excited to show to people working in heat transfer, because I think it might have some interesting applications moving forward. Okay, so this is my group that I started at UNC. I have a bunch of students who keep me busy. I've been very fortunate to recruit very good students. So these are the guys who really did the work. I don't do anything in reality. And these are the collaborators in some of the projects. They also participated here. And we were fortunate to get funding. So thank you also for the money that people give us. It's always important. I wanted to put this slide. This goes back to my PhD times, right? This is what I did in Edinburgh. At that time, I was looking at the evaporation of sessile droplets. And what we try to do is we try to take a step and try to look into droplets that were not axisymmetric, right? So over there, I work developing this two-phase code, and then we study, for instance, the fluid flows, heat transfer, and evaporation of sessile droplets that, for instance, in this case, this is the top view, is an oval shape, right? and the Marangoni flows is kind of interesting what it is. Then we have another case in which we try to simulate a droplet where initially the position was here, and then there was an unpinning of the droplet and the flows that appear. So that's kind of what I did. And then once we realized that there was not much done in this area, there was another paper in which what we did is some experiments and some theory for droplets that were non-spherical, but they will have well-defined shapes. And when you start thinking about that, you realize that on one end, you have something that is axisymmetric, and the most different case is something that, for instance, has a contact area that is triangular. And we study the evaporation flux in these droplets, the coffee ring effect, and it's kind of interesting because now you have the evaporation flux that changes along the perimeter, you have accumulation at the tips, and so on and so forth. And I think this is motivated some research that keeps working on this, and yeah. So that's how it started, right? So this is a kind of an engineering problem. But then I evolved as everything in life. And then kind of now my areas of research are kind of these quantum analogs. This is the first part of the talk that I'm going to try to tell you about, in which we're going to use fluid mechanics or a system, these walking droplets that were discovered in a fluid mechanics course, to try to show effects, quantum mechanical effects that before we thought they were only possible with quantum particles. But this system has some properties that perhaps shows you that we can do much more with classical mechanics. Then also we study with nonlinear waves. These are Faraday waves when you vibrate about up and down. And this is a driven dissipative system. It's very interesting mathematically. And what we try to do is try to harness instabilities that lead to coherent motion, right? So you see in here, the waves are kind of moving around, so there is no coherent motion. But for instance, if you use confinement, or if you use certain shapes, now you are going to see that these waves will start to move in some direction. And you can think of, I don't know, the video is not very good here. Is it? I don't know if the connection, the video should be smooth, but I don't know if we can do anything. Okay, we'll deal with this way then. Okay, so we started also, we discovered these bubbles that we call them galloping bubbles because they start moving. And then we also recently started with an active matter system in which, okay, so sorry about that. This is not being very, it's not cooperating. Okay, let me see. Let me go back. There is some delay because in my computer it's going very smoothly. So I don't know, doesn't matter. Okay, this active matter in which now you have many units that perform a task and you look at the collective behaviors emerging. And we did this, it's kind of also, I think, interesting. All right, so let me get started with this problem, with the quantum analog, right? So what happens when you have a droplet of a liquid and you put it on the surface of the same liquid? What happens is coalescence, which I'm sure you guys are familiar with, in which the droplet becomes part of the bulk in several steps or at once. Whether it is partial or complete coalescence depend on the honest org number and the bond number. If both of these numbers are small, it means that surface tension is the dominant force, and then you will get partial coalescence. You will get this coalescence in steps, right? So now what happens if what I do is I remove the droplet, I take the bath, and I vibrate it up and down vertically. That's all I'm doing, right? So the setup is this one. We have the bath here that we vibrate sinusoidally with some acceleration gamma and some frequency f. And if you have enough acceleration, you will see that there are these waves appearing on the surface of the bath. These are called Faraday waves. For the fluids that we use, they usually appear around 4G. And another thing to remember, just kind of have some detail to remember, is that they are subharmonic. They are oscillating at half of the frequency of the driving, and they are monochromatic. They have a well-defined wavelength. that is given by the water wave dispersion relation. Okay. So now what happens if I take the bath, I vibrate it up and down, and I put a droplet on top, right? That we had before. So now what you are going to see is the video in the first slide. You are going to see that the droplet that before coalesced, now it does not coalesce because of the underlying vibration that in here is hard to see, right? And what you should think is that because of the vibration, there is always an air cushion between the droplet and the bath. So there is no direct contact, and the bath pushes the droplet up, right? So this is a problem that you can study, for instance, the lubrication layer between the droplet and the bath. And you will see that this happens when it has a critical thickness of 100 nanometers. So if it becomes smaller, then van der Waals forces will initiate coalescence, right? But because of the vibration of the bath, you do not let the air layer to drain to such a small thickness. So you always have air there. And then you can study, for instance, what is the bouncing threshold, which is the minimal acceleration at which you need to vibrate the bath to get coalescence, right? And it goes with the square of G, but for instance, perhaps remember in here that is around 1G, right? Okay, what happens now if all we do is we increase the driving a little bit higher, but not as high as the Faraday threshold that excites waves? So this is what I²CNER did, and he realized that the droplets will now start spontaneously to walk along the bath, right? So in this case, you see the droplet is moving from left to right, and this is happening because every time that the droplet impacts, it's creating a wave. Because of the driving of the bath, the longevity, the lifetime of these waves becomes larger. So now the next time that it lands, it will land in a wave produced at previous bounces, right? The wave field grows. And because of that, there is an instability that it starts to land on the slope of the waves produced in the past. And this is what propels it forward, right? It receives a horizontal kick. Okay? So in free space, if there are no obstacles, this will move in a straight line at constant speed. Right? And for us, this is conceptually very interesting because in here you have a macroscopic realization of a particle and a wave, right? I now have a combined object that has a particle but is propelled by a wave. So you can perhaps expect that this system can show these dual wave-particle behaviors that before we thought they were only possible in quantum mechanics. So when this system was discussed, well, just to summarize, right? So this is the driving. We have the bouncing threshold. We have the walking threshold in which the droplet starts to walk. And then we have the Faraday threshold between which waves appear spontaneously, right? We are going to normalize the driving by the Faraday threshold. So now the Faraday threshold becomes 1, and we are going to work in this area, right? Only in the walking region. So the waves that we excite is because the droplet excited them. If I did not have the droplet there, there would not be waves. It's not that I am putting waves there. They are self-excited. The proximity to the Faraday threshold is what we call memory. And basically, this controls the longevity of the waves. So the closer you are to the Faraday threshold, the more the wave field is going to influence the dynamics. So the more you expect this particle to have wave features. Okay? The combined object composed of the droplet and the wave field, this is what we call a walker. This walker has 2 interesting features. It has a special extent, some length, which means that the droplet is going to feel things that are distant. Because if I have some obstacle, this obstacle is going to deform the wave field, and the droplet, which is far from the obstacle, is going to react to it, right? And it also has memory, because the waves persist a significant period of time in the bath. I need to integrate them back in order to be able to predict the trajectory in the future, right? So I need to remember the path. That's what we mean by memory. In general, for you to remember today, both of these features increase with the memory, with the proximity to the Faraday threshold, right? So keep that in mind. Okay, so how you model these droplets to kind of get a little bit of more mathematical intuition. So you will have to consider Newtonian mechanics, right? And you are going to have the inertia term. It's going to have some friction because there is viscous dissipation when the droplet is flying, when the droplet is impacting, right? And then you are going to have a forcing that is proportional to the gradient of the wave field, right? It's proportional to the slope. And this has to do with the force projected into the horizontal direction. Okay, so that's the drag, some during impact, some during flight. Then we have the vertical force and the wave field. So the difficult part is to compute the wave field because you have to integrate back in time. It's a complicated problem, but if you take several limits, if you assume that the droplet is a point impact after a long time, right? You take several simplifying limits. You can show that at each impact, the droplet is producing a Bessel function in the position where it impacted, right? And then you can use, again, several assumptions of the limit, that the waves are linear, that the vertical dynamics are much faster than the horizontal dynamics, and that the droplet is bouncing synchronously, always at the same time. That allows you to simplify the problem. And then you can show that I can compute this wave field as an integral of the Bessel function, which is what is producing at each time, which is decaying with some characteristic time that depends on the memory. So you see, I can change through the memory the decay of the waves. And the integral comes because you bounce very fast relative to the horizontal direction. So instead of having a discrete sum, you can approximate that by an integral, right? Okay, so now that you have the wave field, you can compute the gradient, you can plug it back to the equation, and you will have this equation of motion in which now you get the first order Bessel function because it's the gradient, right? And you have this from the derivative, from taking the derivative. This is what we call the stroboscopic model. And if you look for solutions at constant speed, right, then you can show that this has a solution for that. And this is the expression that you get for the preferred speed, right? So this model has this notion that the droplet wants to go at a preferred speed. You can non-dimensionalize the problem by the memory time. That's the decay time of the waves and the Faraday wave number. And then you will get the dimensionless expression of the previous equation, which is a little bit tidier. And you see that there are two parameters. This is the kappa, which is the dimensionless mass of the inertia, and beta, which is the memory force, how much the wave is pushing it, right? Okay, if you look at the droplet from the top, you will see that this is the wave field. So the droplet will be here at 0, and it will be moving to the right. And this is the characteristic shape of the wave field that it produces. And if you take a cross section, you should think that the droplet is riding that crest, right? That's why it's being pushed. Okay, so now that kind of we have a little bit of a mechanistic understanding of these droplets, why they became interesting for many people is because of this idea of this particle-wave duality. So this whole thing, this whole field of hydrodynamic quantum analogs developed, in which people are interested in using this system, this physical system, to show that classical mechanics can show effects that before we thought they were only possible in quantum mechanics. And there is a growing list of analogs, things like diffraction, quantized orbits, and it's very interesting because kind of before walking droplets, we thought that this was not possible. It was only possible in quantum mechanics. And this is a millimetric droplet, right? Okay, so we are interested in this system because it really pushes the limits between classical and quantum mechanics. So that's kind of the motivation for this problem. I'm going to show you one of these examples, one of these quantum analogs. It's going to be Anderson localization, and this will allow you to kind of understand what I mean. Okay, so I'm going to start to think of a general problem in which I have a particle, a classical particle, that is moving in some random potential. This problem can be a bacterium going through a porous medium. It can be a self-propelled colloid that is going along a track with random obstacles. It can be an electron that is traveling through a metal where there are impurities, right? In principle, all of those fall into this category. I want to think of the problem as universally as possible. I don't want to get lost into the details of each of them, So in all of those cases, in principle, the background, I can model it as some disordered potential, Ux, that will have some characteristic value that I'm going to call U0. And in the simplest possible terms that I can think of, I would say the motion of the particle will be governed by Newtonian mechanics, right? So inertia times the gradient of the potential, okay? So this problem, of course, everyone knows, it has a well-defined energy, which will have a kinetic part and a potential part. We're going to be interested in the case in which the total energy is much larger than the potential energy, right? So the kinetic energy or the total energy is much greater than the characteristic potential energy. So think about this. In this case, you have a particle that has a lot of kinetic energy and is going through a potential that is random, but is weak. So then what you would expect is that the particle can go through the potential, right? But every now and then, it's going to receive a small kick that is going to deviate it a little bit. If you wait long enough, and if you zoom out enough, you are going to see that in the long time limit, this particle is going to behave diffusively. If you look from the distance, right? Okay, so you can do simulations to show that. So this is an example of simulations. And in a random potential that is weak, to quantify this, you can compute the mean square displacement. And in this case, you will see that eventually it becomes linear with time, and the coefficient is the diffusivity. Okay, so that's the general problem that I'm thinking about. Now, what happens if I ask the same question, but instead of having a classical particle, I have a quantum particle? The exact same problem. The answer, in this case, is completely different. This is the wave function given by Schrodinger's equation in the same setting. I have a potential that is random and weak, but is sufficiently random. And you see that the wave function that tells you where the probability of finding the particle is, it kind of gets stuck there. It does not spread, even though the electron has much more energy than the particle. If you look at the mean square displacement of this function that you can also compute, you'll see that in this case, it saturates to a value that is well before the size of the box, right? So in this case, in the exact same conditions, the quantum particle does not show diffusion, right? There is this absence of diffusion, and this is what is called Anderson localization. This is a very important quantum mechanical effect that was discovered for electrons going through metals with impurities, right? So no matter how weak the potential is, if I have enough disorder, this particle is going to become stuck spontaneously, which is very counterintuitive, right? Okay, so how do you understand this mathematically, the quantum mechanical effect, before I show you what we did with the walking droplets? So you are going to take a Schrodinger's equation, in this case I've non-dimensionalized it, and we are going to take the time-independent part of the Schrodinger equation. So I'm going to have the eigenfunctions and the energies, right? And we know that these are discrete. And I'm going to plug some potential that is random. The specific details of the potential are not too important as long as you have randomness. And then if you think about the problem, what I have, I'm always considering the case in which the energy is much larger than the energy of the background, right? So if I rearrange this equation, I have something that is a second derivative equal to minus some positive quantity times the function. So you would expect to observe oscillatory solutions, sines and cosines, with some deformation given by the local features of the potential, right? So you would expect to have scattering states. The electron should be able to go everywhere. It has a lot of energy. This is not what you get. What you actually get is that the eigenfunctions are exponentially localized in space, right? You see, you have peaks. They are not extended states. They are localized states. They are confined states, right? So why this happens, this is Anderson localization, the quantum mechanical effect, and the manifestation. And why this happens mathematically, for instance, is very interesting because it's counterintuitive. Why this happens. And there is a lot of research going on in here. Okay, so, but because this is the explanation of the quantum mechanical effect, it comes from this equation. This equation, you find it in many classical waves systems. So then this is attributed to the wave-like behavior of quantum particles, okay? When people realized about this, they were like, okay, I should be able to observe this effect in other systems. And they study this localization with microwaves, light waves, ultrasound, matter waves, water waves. They are all classical wave systems, and they found it. Okay, so now the perception is that Anderson localization is a classical waves phenomenon. This is, if you read the literature, this is that you are going to learn. Yes, but we're forgetting something. In the quantum mechanical case, there is the notion of a particle. The quantum mechanical case is different from this one. In here, there is no particle. In the quantum mechanical case, if I look, I see a particle. I don't see a wave, right? So that's the question that we are posing in here. Do only quantum particles exhibit Anderson localization? This is the question. And so far, we are being told that yes, this is only possible in quantum particles. Okay, so what we did is now we consider one of these walking droplets, and we put them in a setup in which now the topography is random, right? So now the droplet is going to fill the topography, and it will have some base depth h node. And around this, we are going to have tiles that will have some random height drawn according to a uniform distribution. Right? And we are going to be looking at the high memory to maximize the wave behavior, right? So we are going to do some random realizations of this topography. We are going to do many of them. We are going to 3D print them. And then we are going to put this into our vibrating table and see what the droplet does in this case. Okay, so this is the experiment. The droplet that before was moving in a straight line now is moving erratically because it's filling the topography. The topography is deforming the wave field, and because of that, this droplet now is moving around in somehow a chaotic manner, right? If I change the lightening, you can see the topography, right? The droplet, even though it's very, very small, is reacting to those random steps. And just keep in mind that for us, the topography is going to be playing the role of this potential. Okay, so this is the experiment with the walking droplet, right? So this is the post-processing of the droplet. You see that this is the top view. The droplet is exploring the domain. It's showing some preference for the top right in this particular case. But other than that, it's chaotically moving throughout the domain. It should be able to move because if the domain is, the topography is very weak. You have to record this for a really long period of time. And if you do that, you get enough data because you want to compute a position histogram, okay? And you want it to be statistically meaningful. So now that we have this data set, all we do is we compute a position histogram. And what you get in this case is that there is a peak, much like the one in quantum mechanics, appearing in the top right corner, okay? But anyone who has done experiments will ask quickly, is that because there is a bias? Is it going to the top right corner because there is a bias in the experiment, right? Of course, we also ask ourselves that question. So in order to answer that question and to do other things, we did simulations to go with the experiments, right? So in the simulations, now the model that we have to use is a little bit more complicated than the one I showed you. I'm still going to have a droplet trajectory that, again, it has the same part. It will have the inertia, it will have some friction, and it will have the forcing given by the gradient of the wave field. In here, we call it eta instead of h. But now, eta, I cannot solve it analytically. I have to solve it with numerically, right? So what we have to do is we have to have a couple PDEs to solve the interfacial problem. So this, you basically use a quasi-potential flow and do some simplifications. So this will be the potential, the evolution of the potential, the velocity potential at the interface. You will have variable gravity because you are vibrating. So effectively, you are changing the gravity. You have the surface tension term. You have some dissipation. And you have P. This is the pressure exerted by the droplet on the interface every time that it impacts. And then you have the evolution of the wave field, of the interface shape. This is eta T. That is given, you have some friction there, from viscosity. And in here, typically, if you kind of remember water waves, in here you will have the gradient of the velocity potential in the z direction. In this case, we replace that from an approximation from shallow water theory, in which you replace that operator by an effective depth that is computed from the actual depth that basically gives you the right dispersion. Okay, so now I'm gonna have an effective depth at each position of the domain, and that's how I'm gonna take into account the topography. And we're gonna assume, for mathematical reasons, that the impacts are delta functions in space and time, because if not, it's very difficult to do. Okay, so that's the model that we have. Here, I put a summary of the experiment, what we found, right? This is the experimental realization. And now I take the model and I repeat the same thing in the same parameters. And what we get is that you also observe a peak in the top right corner, right? With some differences because there are simplifications. But the main point is that you get also something happening on the top right corner. So there is something special about that. It's not experimental error, right? Okay, so now what we can do also is, what will happen if I take this potential, the depth that I mentioned that we know how to interpret as a potential, right? I take the exact same one. The only thing I do is I rescale it because I need to make sure that it has more energy. And I plug it into a Schrodinger's equation and I ask which one is the first mode. And I do that just because we can. In math, we can do anything that we want. So if you do that, what you get is that a quantum particle will show localization in the same area, right? And we are very interested about this coincidence. In this case, we just did it to see what it will happen. Now we are trying to understand why there is this connection between the two, right? Because it cannot be by coincidence. So now we are doing more theory to understand that. And again, to put things into perspective, what will happen if I did the problem in which now I have a particle, but it does not have a wave field? The case that I started, right? If I have a classical particle given by Newtonian mechanics without the wave field, then what I will get is a histogram that is uniform. And this makes sense because we said that the particle has to have much more energy than the potential. So you expect that the particle is basically able to move everywhere and explore the domain uniformly. That's the manifestation of that, right? So you see, walking droplets, because of the wave field, shows an effect that is very similar to the quantum mechanical effect and is very different to what you will get with a particle that did not have the wave field, right? So far, we only knew this, and we were told that this is impossible with classical mechanics. Now walking droplet suggests that it's not impossible. Okay, with the simulations, we also did them because now that we have confidence in our code, we can use it to do simulations in domains much larger than what we can do in the lab. And this is what we did here, right? Now we consider many different realizations of the domain much larger at high memory, and we put a sample, an ensemble of particles. And if you wait long enough, you will see that the mean square displacement, it saturates. But remember, kind of the memory is kind of like my knob in which I go from at low memory, something without a wave field, at high memory, a particle without a wave field. I can control it, right? So we did that. We just reduced the memory in the same problem. That basically means reducing the influence of the wave field. And if you do that, now the particles, because they have almost no wave field, they behave like classical particles, and you get a mean square displacement that goes very, very large, right? This is the diffusive behavior. So if we do that for different memories, in here, we can see that the memory allows you to have a transition. So you look at the mean square displacement, right? And the part when it's straight, you wait long enough to make sure that you are in the diffusive part. And now you look at the exponent of the time. If the exponent alpha is 1, it means a diffusive process. If the exponent decays, it means that you are suppressing diffusion. And this is the exponent. And you see it goes from 1 at a low memory, and it becomes very small at high memory, right? So this memory that controls the wave field is suppressing diffusion in the system. And we'll skip that. What I wanted to say is that even though there is no diffusion, the particle keeps moving. It's doing loops, right? So it's not that the particles come to a halt. In order to understand the mechanism of this, you can look at the Faraday waves. So if now I take the experimental setup and I cross the threshold, I will see that the Faraday waves take this shape. Right? These are the Faraday waves without the droplet. And the droplet, what it's doing, so that's where the waves are, that's where the experiment localized, that's where the simulation localized, and that was when we plug it into the quantum case where it localized. But what I wanted to show you is that what the droplet does, this is the droplet, is acting like a moving delta function that is exciting that wave field in a strange way. And when the droplet is near the localization region, it resonates with the Faraday mode, becomes larger, and draws the droplet in. And once the droplet is inside the localization region, it's resonating with the mode of the cavity, it's really exciting it, it's making it very large, and that what it causes is to create some loops there, right? So the kind of the two things to understand the mechanism is we call it a Faraday beam. When it's far, it resonates with the mode, and that's what draws the droplet into the localization region. And once you are in the localization region, the droplet resonates with the mode, it's exciting it at the right frequency. It excites very large waves, and that causes the droplet to kind of stay stuck there. You can do this with simulations, but I'm gonna skip this because I also want to get to the bubbles. And the last thing that I'm gonna tell you about this project is you can get, this is what I show you is the instantaneous mechanism, right? The droplet goes in and kind of gets stuck. Can I give you an explanation of the statistical behavior? Why it stayed there, kind of on an average sense. So in order to do that, we took the simulations and we compute what is the mean wave field, right? I can do that with simulation. And this is that the mean wave field that the droplet excites after spending hours there. And we look at the spectrum of this mean wave field, and we saw that it has the Faraday wave number. This is the preferred length scale that I mentioned initially. We expected that. But in this case, it also has these long waves that typically don't appear in walking droplets. And mathematically, what we can do is we can, because the wave problem is linear, we can delete these waves and reconstruct the wave field that we will get from the PDF and these long waves, and to see what shape that will do, right? This is what we do. We basically do a convolution of the long waves with the position histogram. And that will tell me what these modes contributed to the wave field. And if you do that, you will see that it gives you a long range envelope, right? This is a depression in the localization region. On average, the droplet is creating a crater there. And that's why the droplet keeps going there. And that's why it populates that area more and more, okay? Okay. So this is the coincidence that we found. We are very interested in this. We are doing much more research to understand this even more deeply, this coincidence. But yeah, this is the first part that I wanted to mention. You see, this is a more mathematical and more curiosity-driven research, right? In here, we don't look for applications. Now, I'm gonna go to the second part in these galloping bubbles, which is more an engineering problem, right? And at the end, I'm gonna try to show you what we think it might be you can do with these bubbles. Okay, so I guess I don't have to explain to you why people care about bubbles. This audience should know this very well. In other departments, I have to explain to them. So people care about bubbles for many, many things. Some people care about bubbles just because of the dynamics are very fascinating, are very interesting, right? That was the case, for instance, of Da Vinci, who saw a bubble rising, and the spirals that the bubble did caught his attention. And this is what is being called the Da Vinci's paradox. Why a bubble that it could go in a straight line, it starts doing spirals. And there is still ongoing research. So that's a motivation. Another motivation could be just because it's very ubiquitous. You see bubbles everywhere. You see bubbles in drinks. You see bubbles in when you wash your dishes, right? So it's something that we see very presently. So that's another reason why people care about bubbles. People, and perhaps here this is more what you guys like, care about bubbles also for applications, right? So for instance, in boiling, bubbles are generated. You want to cool down some device. And if you are on Earth, you have buoyancy to help you, right? The bubble is generated in the heating object. You want to remove the bubble. Buoyancy naturally was going to help you. But what happens if you are in the International Space Station or a satellite, over there you don't have gravity that you're going to push it away. So would it be interesting to have some mechanisms that allows you to evacuate the bubbles? So that's something people care about, that, right? Okay. So if you now think of the problem of what happens when I excite a bubble, when I vibrate it periodically. So this has been done a lot. People vibrated a bubble vertically, and you can find very interesting phenomena. For instance, in this case, you can make a bubble go down against gravity because of the vertical vibration. This is due to Bjorkian forces. People excited bubbles also with acoustic waves in the context of cavitation. This is very interesting, right? And there has been a lot of research in which, for instance, people saw that the bubbles move erratically, move chaotically, and this is what is called the dancing bubbles, right? And in other cases, there was Longer-Higgins thought, what will happen if I move a bubble up and down, and at the same time, I make the bubble grow and reduce in volume? This was a theoretical problem. And in this case, he said, like, you can make the bubble go vertically, right, in the direction of the motion. So if I think of all of these problems in which there is periodic forcing of a bubble, I'm going to say that I have motion in the vertical direction, parallel to the driving, or erratic motion. Can we, our question was, can we induce coherent motion perpendicular to the driving? This is not of the cases here, right? Can I make a bubble vibrate up and down, but the bubble move perpendicular to the driving? And if I can do that, what can I do with that bubble? That's kind of the motivation of this problem. Okay, so the problem in this case is, and this came from a mistake that we made, and we were lucky that we realized we had a bubble that it was stuck inside a fluid chamber, and it was stuck against the top wall of the fluid chamber by buoyancy, right? So this is the setup. I have a solid wall and a bubble. And this bubble had a characteristic size that it was comparable to the capillary length. Or in other words, the Born number of this bubble was around 3, which means that the bubble was going to be deformed a little bit by the gravity, but not too much, right? It has some deformation. Now we are going to subject this setup to vertical vibrations. That's all we are going to do, right? So the problem is symmetric in the vertical axis. So we put it in the fluid chamber. The fluid chamber has all the other walls too far, so they don't play a role, right? And we put it into the same shaker that has very precise vibration, and we see what happens. Okay, so this is what happens when you vibrate the bubble at a relatively low amplitude. The bubble, the vibration effectively, what it's doing is changing the effective gravity in the moving frame. And because of that, you have these oscillations up and down that have the same frequency. Right? This bubble, these oscillations are symmetric, meaning that left to right is the same thing, right? And the bubble stays there. So if you have perfect leveling, the bubble does not move. What happens if all I do is I increase the driving? I'm not changing anything else. The problem remains left-right symmetric. So something fundamentally different happens. Now the same bubble, I've only increased the driving. This bubble starts to move from left to right in this case. And it does it in a way that for us, it was reminiscent of galloping motion, right? It looks like a little bit galloping motion. So that's why we call them galloping bubbles, right? So there is a spontaneous symmetry breaking. Even though everything is symmetric vertically, the bubble breaks the symmetry and goes laterally. This happens beyond a well-defined threshold, right? It's an acceleration beyond which this happens. This is what we call the galloping threshold. It's the equivalent to the walking threshold in the walking droplets, right? Okay, if you look at these bubbles from the top, you are going to see that they are going to move typically in a straight line, and kind of it can go quite random direction. Sometimes they bend a little bit, but in principle they can go in a straight line, right? Is this the only way in which the bubble can move in a straight line? Turns out that no, you actually can get these bubbles to do other things. So depending on the size of the bubble and the frequency and the driving, you can get the bubble to go kind of in a straight line until it meets a wall and it moves away. In other cases, if you increase the driving, the bubble starts to do orbits, spontaneous orbits, circular orbits by itself. If you increase even the forcing a little bit more, the bubble will move erratically. This is what we call the ram and tumble motion, right? In which the bubble is moving kind of chaotically around the domain. Okay, so you observe all of this. So we characterize all of the system in terms of the bubble volume and the displacement of the bath. That's the driving, the acceleration. And we found these behaviors, right? So this will be the rectilinear, then we have the orbits and the run and tumble. And then we also had some additional dynamics. So in some cases, the bubble will detach from the top wall, right? Will bounce off the wall. In other cases, if the driving is very large, the bubble will eventually break up, right? You will have some ejection of bubbles. And just here to point out something that the speed of these bubbles is very, very fast. So this is not a marginal effect. They really move fast relative to the driving. Okay, so if you in here we fix the frequency and we vary the volume, I could have picked a volume and I could have varied the frequency. You end up getting the same dynamics. So that tells you that these two parameters collapse into some dimensionless number. This is captured by the Weber number that has the frequency embedded there and the size embedded there, right? So the Weber number, you should think of it that is either I'm changing the frequency or I'm changing the volume, the size. So now what we are going to do is we are going to rewrite this phase map in terms of a normalized driving relative to the size of the bubble and then the Weber number. And I'm going to already tell you that I mark here Weber number 40. And this is going to be important, right? So keep in mind that kind of the first time that I see motion is around Weber number 40. Then there is shifts, but the lowest driving I see there. Okay, so what is the mechanism of this instability? So that's the problem that the mechanism has, is that the base geometry, when there is no driving, is very complicated. Mathematically, this is very hard. I don't know what is the vibration mode of this bubble. It's very, very complicated. So something that we try to do is we try to think like remove details, right? For us, it's very important to remove difficulties that are not essential. So in here, after being stuck, we thought about this and we were like, is it really important? Is it really this shape important? Is it really, are the details of the geometry that important? And then we ask our question, what if I had a hemispherical bubble? Because if I have a hemispherical bubble, the problem simplifies dramatically, right? Because now the geometry is a nice geometry where I can use spectral decomposition. I have harmonic functions that are orthogonal. So that's our thought. We were like, it's not too difficult. It's not too different. Would it do this? Okay, so in order to see what happens there, we went back to simulations. And these are direct numerical simulations that we did. And in the first case, we took the code and we tried to simulate the bubble in the experiment to make sure that we have the right dynamics, right? To benchmark the code. And we captured the same configuration as in the experiment. But then, if once I have certainty that this code does what the experiment shows, I can take the code and I can change the boundary conditions. And now I can have a hemisphere with a moving contact line at 90 degrees. And I can ask the question, will this hemispherical bubble gallop? And it does. So then the simulations show us that the details of the geometry are not essential to understand why this bubble gallops, right? So we compare them side by side, right? What we call the full bubble and the hemispherical bubble. And we did the simulations, we compared them with experiments. And in here we didn't have experiments, but we put the simulations. And again, there are some shifts, of course. You are changing the geometry. But the main feature is that you observe, again, in the same order of the parameter motion. And again, it's kind of around 40. Kind of, there is a tone here that appears, and it's kind of started at 40. Right. So now that we have this coincidence, what we can do is I can go back to the simplest problem of bubble vibrations, which was worked out by Rayleigh, in which he basically studied if I perturb a bubble in a potential flow, viscosity is not important, how the bubble will recover itself, of what modes it will show. And in this case, you can represent, because you have a nice geometry, the perturbation of the bubble as a sum of spherical harmonics, right? And this is an orthogonal basis. And Raleigh work out what will be the resonant frequency of each mode. At what frequency each mode will resonate and will grow. That's the Rayleigh condition that he figured out, is that this Weber number will depend on the order of the spherical harmonic, right? Okay, so why I do this? Because now our bubbles have the same problem as Rayleigh, because I have the nice geometry. The only thing that I have to do is I have to restrict the spherical harmonics. I have to have the ones that in which K plus L are even. Those are the ones that are perpendicular there. And those are the ones that I'm going to enforce that I will have a 90-degree contact angle, right? So basically, I'm solving Rayleigh's problem with half of the modes. Think about that way. And if I do that, I can now take the simulations and I can get the data and I can project it into the modes. And I will see that the galloping motion is dominated by 3 modes: the 2-0 and the 4-0 that are symmetric, and the 3-1 that is asymmetric, left to right. And if I now use Rayleigh's equation, I can compute the frequencies at which I should see those modes, right? The resonance frequencies at which those modes should appear. And look what happens. The Weber number, 40, is the resonance frequency of the 3-1 mode that is asymmetric. So you see there is a correspondence. We see motion where this mode should appear. So obviously this is pointing at this mode as the reason why the bubbles walk, right? So you can do this quantitatively, and again, every time that you see motion, the 3-1 appears. You do not see motion unless the 3-1 is there. So the 3-1 is the suspect here. Okay, so we did, after this, because we are in math, we did the full asymptotic theory of this. And this is a complicated theory in which you have to, again, take the geometry and you have to take limits, right? So we do it in the small ball number. That is going to mean that the bubble is nearly spherical. There is only small perturbations. This happens in nearly implicit flow. So the Reynolds number is relatively large. So viscosity is playing a weak role, but you need it. And then what we have is this is the displacement of the bubble relative to the size of the bubble. This is very small. So we're going to use this as a small parameter for a perturbative theory. So the equations, once you massage them, are these. This is the equations of the problem, in which you have potential flow in the bulk. And this will be the boundary conditions, the dynamic boundary condition and the kinematic boundary condition, right? Phi is the velocity potential, whose gradient will give you the velocity. And we are going to have some dissipation using the viscous potential flow kind of theory, because if not, the bubble is going to blow up. You need to have some dissipation. This term is going to be the gravity term, but it depends on T, right? This is again the forcing of the equations, and that's basically it. And some technical difficulty. This cannot be written in Floquet form. I don't know if you are familiar with that, but you have to do multiple scales. So then you have all of those equations, and now you expand the bubble interface in terms of the small parameter that it will be the driving, and then each solution at each order will be an expansion in terms of spherical harmonics. You do the same thing with the velocity potential. Here you have to maintain the R dependence because this is not a surface, it's a volume, right? Then you also have to expand the Weber number because the Weber number is the resonant frequency, and we are looking for a boundary in which the solution does not grow. So we need to, that's what is going to tell us that boundary. And then we have to use multiple scales because we cannot write the problem in Floquet form, right? So we're going to have to use that slow scale to get the resonant conditions. If you do that, go order by order, you will see that to lead in order, you get that what I'm interested is the equations that govern the amplitude of each term. And you will see that at first order, you have something that is like a driven damp oscillator for the 2-0 and the 4-0 mode, which means that this is going to be forced, but it's going to be bounded and it's going to resonate at the frequencies, right? It's going to become larger. And viscosity, what it does, if the viscosity goes down, it means that these resonances are larger, but they are bounded, right? And then if you go to higher orders, and if you look at this 3-1 mode, what you are going to see is that there is a tone that appears from the 40, and this beyond this tone, this mode becomes unstable, right? And if the viscosity goes down, you basically reduce the threshold. So this effectively is our galloping threshold. And when we put here the simulations that move with the hemisphere, you see that the simulations fall there, right? So now we understand the mechanism also mathematically. The droplet starts to walk because this mode is parametrically excited and becomes unstable. And then some nonlinearity will stop. Just I'm very close to finishing. Once you have the shape, you can ask the question, okay, I have an asymmetric shape. Why it moves? What propels that? And because this is in nearly inviscid flow, this is moving because of the mechanism pointed out by Sáenz, so it's moving in potential flow, right? And just my last slide about the mechanism. Look at the subtlety here. If I only had the 2-0 mode, this bubble will not move, right? Because it's symmetric, right? It's not going to have anything laterally, right? The same thing is happening to the left and to the right. If I only had the 3-1 mode, this bubble still will not move. Because by the mechanism of Sáenz, this is like a swimmer, right? If I do this in one stroke and I do this, I advance a little bit in half of the period, but I recover it in the other half. So I will not move. So this by itself cannot make the bubble move. It will move back, forth and back. So it's the coupling of the two, the coupling of the base state that appears the minute you start driving, and this mode that becomes unstable, the one that makes the bubble asymmetric and makes the bubble move forward, right? So it's the coupling between the two. It's not just the 3-1. Okay, I'm just going to show you just nice videos to finish with this. This will be some applications that we thought, now that we understand this, what can we do with these bubbles? You can now think of mechanisms to remove bubbles, right? And this is going, in this case, we didn't heat it up, but in this case, we were thinking about the boiling problem, right? You have some heating element in which a bubble is created, and now you assume that you don't have gravity. So this allows you to remove the bubble left and right. It can allow you to remove it. So for instance, we think that perhaps this may have some application in boiling processes. You can now think also of this mechanism to create bubbles of different sizes, which is not a trivial task, because I have now a nozzle in which I am introducing a constant rate, right? And if I tune the frequency, basically I make bubbles gallop at different sizes. So this basically says when the bubble reaches some critical size, the galloping mechanism, it will kick off and it will move away. And if I change the frequency, I change the size at which that happens. Okay, I can also think of ways of self-sort bubbles by size, because what we saw is that these bubbles want to follow the walls. So now I can just put them in a channel in which I have different collectors of different sizes, and you see, they go, the smaller ones go first, the medium size will be self-collected there, and the last one go to the end, right? So this is a mechanism for self-sorting. We put them in mazes, and we ask ourselves, will they be able to solve the maze? This one was very close, but they missed it. But eventually, all of them are able to find the exit. With this, what we wanted to show is that these bubbles can navigate very complicated flow networks, right? And the last one, do you guys have a cleaning robot at home? So this is our cleaning robot. So this is a surface in which there was dust, dirt on the top surface, and we put a bubble there. And we ask ourselves, if the bubble is creating these flows and is moving around, will it be able to remove the dust? So eventually, if you compare the beginning and the end, you will see that you can also perhaps think of mixing or removing parts. Right? So that's it. Thank you very much for your attention. That's the two kind of problems that I wanted to show you. I hope I spoke clearly enough. I apologize if I didn't. And yeah, I'll be happy to take any questions that you have. Thank you.
So very beautiful work. And I think I'd like to start from the on-site audience. if you have any question. Oh, that's cool.
Thank you very much for your interesting talk. So I have one question about the, maybe there is a half of your talk. So you show the difference between the experiment and the simulation, the droplet on the water surface. And I see some differences.
Yeah.
And if my memory is correct, so in experiment, the path is not only the top right, but also is moved like left. Oh.
Perhaps I can
Yeah.
go back to that slide very quickly. This one?
Yes. Yeah, so in the simulation and yes, so I'd like to know what causes a difference, especially for the path on the left top side.
Top left, why it goes more or less there?
Yeah.
So in this case, I just want to point out that this is a short trajectory, right? The trajectory is much longer. So this is a small region. So this does not mean that this droplet didn't go there. This droplet went there at a different time, right? So at the end, you see that here is not perfectly blue. There is a little bit of white. So they go, but it's true that they go a little bit differently. So the reason why is, first of all, the system is chaotic, right? So it takes random paths, and you have to explore it for a long period of time until eventually you get the same behavior. But also, there are many simplifications going to this model, because do a full numerical simulation of the experiment is very, very complicated. So we have to do simplifications, like, for instance, the particle, we assume that is a point, a delta function. In the experiment, it's not a delta function, it has some finite size. In the experiment, the contact happens over some finite interval, right? The droplet is in touch with the bath for some fraction of the period. In the simulation, because of mathematical reasons, we also assume that it's a delta function in time, so it's instantaneous contact, right? All of those differences for sure lead to all of those assumptions for sure lead to differences. But what we try to do is try to kind of keep in mind, are we getting the main effect? And accept that we are not going to get everything exactly, but that's the price that we have to get, because if not, these simulations are impossible to do, for instance, with direct numerical simulations. It's too complicated.
Okay, thank you very much.
Thank you.
Another question.
Thank you. That slide, thank you very much for really interesting talk. And about the simulation classical model, if you put the droplet in the same place, so then always the droplet motion should be the same, right? And even if the potential distribution is random. And so how that is really curious. And but it's the result similar to the quantum physics results. And how can we understand the results of simulations? So
the simulations,
anyway, always we can repeat that motion correctly if you start at the same point.
If you start the same point, the exact same initial conditions, the classical system is deterministic. It will get you to the exact same end, but it's chaotic. It's chaotic. The system is deterministic, but it's chaotic also. It means that tiny distributions, tiny variations, is going to take you to completely different paths.
So
right?
that depends on the initial condition, right?
In the initial conditions. And what we do to get a meaningful distribution, not to get any result that is based on some well-defined initial condition, to prevent that, what we do is, in the simulations, we initialize many particles from many random positions to get something that is not biased of the initial condition. And then, because of the system is chaotic, you realize that no matter where you started, actually you get the same histogram eventually.
That depends on the distribution of the substrate. And
the initial conditions is exactly true what you said. If I start two simulations in the same point, they will give me the same result.
Yeah.
And to prevent that, because that would be biased results, right? That would be that we are picking the results. What we do is, like, we don't do that. We do random simulations, many of them, and look at the statistical average.
how many particles did you use in the simulations?
Oh, sorry. So the simulations, each simulation is one particle, right? Because there is no interactions, but we have hundreds or thousands. There is so much data. We have like simulations running for months to really.
I see.
And we also have something that I have not pointed out. We have many different realizations of the topography, right? In here, I illustrated with one just to help, but in reality, we do this with many different random realizations to make sure that these choices are not influencing the results.
I see. Thank you.
Thank you.
I can maybe follow Professor Miyadaki's question, because I noticed that in your simulation, you are using classical equations for mechanics, for fluid and flow. So how can you relate these classical equations for fluid and flow to the Schrodinger equation? Because that is for the statistics. Is it possible to relate the classical mechanics to the quantum?
That's the question, not of my project, but of the field. This is a question of the field, right?
Sure.
This is if that connection could happen, because this goes back to the work of the Prof, who is a guy who participated in the development of quantum mechanics. The Prof had in his mind, what if instead of accepting this interpretation of quantum mechanics in which you cannot ask what to produce the wave function. You start from the wave function, but you cannot ask, was it a particle, was it a wave? The Prof envisioned, what if I had a particle in resonance with a wave, right? And this, what it's trying to show is it possible that there is some connection that we could not work out before because there was not this system. So this system, why it became important is because it motivates something, right? But another thing that we think about is like, eventually the fluid equations might not be the equations that make that connection if it existed. It might be a generalized equation, right? Because why has to be the fluid equation? Why there are many waves equation? So that connection is very interesting. So for instance, for us, the next step that we're trying to do is we are trying to do theory on this model to try to rationalize this connection. Try to rationalize because we don't think that but if this were by chance, we don't believe in chance, right? So try to connect these two. And that's really the big time question. Can we connect a deterministic pilot wave system with the statistical behavior given by a Schrodinger equation? This is really the big question that we're trying to address. At the moment, I don't know the answer. If I knew the answer, I would have shown you because I would be very excited. But yeah.
Okay. You can.
Online? Question online?
Yeah, there's a question online. Can you unmute it? I noticed that there is a question online from Dr. Tam. Can you unmute it? Yeah. Okay. So Dr. Tam, can you hear me?
Yes.
Yeah, sure. Please.
Okay. So thank you for the opportunity. So first, I want to know the difference between droplets and purples, because is it on air purples in water is called purple, and a water drop in air is also called purple. So what is the difference between them?
I understand the question.
The quality drop.
Can you repeat your question or?
Sorry. Can you hear me?
Yeah, sure.
Okay. So I will repeat. I want to know the difference between purple and the droplet. Is it because on air bubbles in waters is called the purple, and a water drops in air they also call is a purple. So what is the difference between purples and the droplet?
Between bubbles and droplets.
Difference between bubble and droplet. Okay, that's a general.
Sorry, I don't understand. So we call droplets when you have a liquid surrounded by air. So what is inside the spherical object is a liquid. That's what we call droplet. And bubble is the opposite, right? When you have air is what is inside the sphere surrounded by a liquid. Is that the answer?
Okay, I understand that, but they are different kind of book. They say different things. So okay, I will check that again. So for my second questions regarding the acoustic cavitation. Acoustic cavitation. So like when the bubbles collapse, they will create the localized hotspots with very high temperature and high pressure.
Correct?
And from there, we can get like strong force or strong shock wave. But the thing is, if I want to get higher force and higher shock waves, is there any way to understand how to control that, how to control the purple cycle or the dynamics of purple to get higher shock waves or higher force?
So I'm not an expert on cavitation. For us, we work in a regime in which cavitation does not happen. Relative to cavitation, our excitation of the bubble is much weaker. So we never, actually, for instance, our theory is all incompressible flow. So in reality, the flows are very mild relative to the flows that you have in cavitation. So we are in a regime that is very far from cavitation.
Okay. Okay, thank you.
Thank you.
Thank you very much.
Okay, so I noticed there's one question in the Q&A section. He asked that, would you mind telling me that you calculate when you calculate about quantum effects, whether you consider in the curvature of the Gaussian plate or not?
Curvature of the Gaussian plate.
Yeah. I understand what he means. When you calculate, I think this is calculate about the quantum effect, but you consider the curvature of your.
I don't know this effect. So is this an effect in quantum mechanics?
Yeah.
Or I'm not sure.
Okay,
what this person is
so
referring to.
Dr. Nakahara, I'm not whether you are an expert in quantum mechanics, or if you would like to talk. Oh, that's okay. I think maybe he's fine with. Okay, so that's it. So, any other question from the audience?
I have one question. Coming back to this slide, I was wondering if the distance between the surface and topography affects the working droplets, mean localization, or no matter what the distance is, localization purely depends on the pattern of the topography.
I mean, the depth.
Yeah.
Yeah. So that's very good. That's a very important parameter. And I already showed you the effect in which this is best. So what happens is, if now I do the same problem, but I separated the topography, eventually you go into the deep limit, right? Which means that the bottom is so deep that the droplet will not feel it, right? So if it's very, very deep, the droplet will not see what happens at the bottom. So I will lose the topography. If I go in the other direction, if I now make the topography closer and closer, the potential becomes stronger and stronger. And eventually, what happens is that you go into the regime in which the energy of the particle is not large relative to the potential. So then the potential is going to trap the particle, right? So we have to be in that intermediate regime. We cannot have it very close, because then I will see localization just because I have a very strong potential. What is interesting about Anderson localization is that you get localization in a regime in which the potential is weak. So the particle should be able to go everywhere. So that's why we have to be in that intermediate. So yeah, very good question.
What's the threshold of the distance where droplets can feel the topography?
In order to the typical depth that we use is comparable to the wavelength of the waves excited. That's the typical wavelength. To define a threshold, we need to do theory, because if not, it looks like a uniform transition, right? So to define a threshold, I cannot define it mathematically precisely, but in order of magnitude, it's comparable to the wavelength of the waves.
No, all clear. Thank you. It's really fascinating.
Thank you.
Okay. Okay, thank you very much. I think, yeah, so that's all about today's talk. So let's thank again to our audience, and thank you very much. I'd like to close this talk.